that we talk about the notion of differentiation of functions into variables. Now for that, we recall the definition of the concept of differentiation of functions in single variable. Recall what we had done is that we had domain D, a function, a real valued function on D. So D is a subset of R, as we are talking about single variable functions here, and we take C an interior point of our domain from our domain. Now, if is differentiable at C, then the derivative of f at the point C is defined to be the limit that is mentioned here. So it is limit as h tends to 0 of f of c plus h minus f of c divided by h. Now the question arises that whether we can generalize this definition to functions of two variables. So let us now talk about our first trial to this end. So now again, suppose D is a subset of R2, which is going to be the domain of a real valued function that we are going to talk about. And as always that will when we are talking about differentiability, x0 y0 be an interior point of the domain. Now a straightforward generalization of the definition of differentiability in functions of one variable would lead us to the following expression. So we will take f of x0 plus h comma y0 plus k minus f of x0 y0 divided by the tuple hk, and we are going to consider the limit as hk goes to 0 0. So we have talked about limit as hk goes to 0 0 of functions, but the problem here is that we do not know how do we divide by a vector. In particular, how do we divide an expression by a two tuple? And what turns out is that such a division is not defined. This leads us to our second trial. So let us now modify our definition of differentiability in one variable as follows. So suppose that we have everything in our hypothesis that we have mentioned, that D is a subset of R, f is a real valued, so D is a subset of R2, f is a real valued function, so here it is R of course, so f is a real valued function on D, and that C is a point on D which is an interior point. Now having all this hypothesis, all these assumptions with us, let us try to do some modification with the limit that we had. So suppose that f is differentiable, then or f is differentiable at the point C. So then we had f prime c, that by definition is limit h tending to 0 f of c plus h minus f of c divided by h. What we can do is that we can write f prime c as limit as h tending to 0 h times f prime c divided by h. This is allowed. There is no harm in writing like this. And then if I take this over here in this side, what we get is that this is equivalent to saying that limit h tending to 0 f of c plus h minus f of c minus f prime c times h divided by h is equal to 0. So this is one notion of differentiability. So f is differentiable at c if and only if this limit is equal to 0. If we modify this a little, we will see that this is equivalent to the following expression: f is differentiable at the point c if and only if the limit h tending to 0 f of c plus h minus f of c minus f prime c times h, so here alpha is equal to f prime c times h divided by modulus of h is equal to 0. Okay, so what we have seen is the following: f is differentiable at the point c if the following limit is equal to 0. This leads us to our second trial. So what we do now, we have two variables x and y. So again, suppose that we have everything that we had in our assumption. So here the assumption was that D was a subset of R2, x0, y0 in D an interior point, and f is a real valued function on D. So then why don't we evaluate this limit? So of course the first term we need to be f of x0 plus h comma y0 plus k minus f of x0 y0. Now here we had one variable, so to speak, h, and here we have two variables, that is h and k, which come here, and then we just replace this expression alpha h by alpha h plus beta k. So what we are going to do is that we are going to replace alpha h by alpha h plus beta k. So we write that on the numerator, and in the denominator what we do is that we simply take the norm of the vector h comma k and we let hk tend to 0 0. And what this definition over here says, or at least motivates us to say, is that if there exists alpha and beta, both real numbers, such that this limit is equal to 0, then we may call the function f to be differentiable at the point x0, y0. So in fact this turns out to be the definition that we are always going to use. So as always, so we have a domain inside R2, we have a real valued function, so the function in two variables and an interior point x0, y0. We say that f is differentiable at x0, y0 if there exist two real numbers alpha and beta, such that f of x0 plus h comma y0 plus k minus f of x0 y0 minus alpha h minus beta k divided by, so under root h square plus k square, that is equal to 0. And you may recall that this is nothing but the norm of the vector hk as we have defined earlier. So this is going to be our definition, and if it is indeed such a case that f is differentiable at the point x0, y0, then we say that this pair alpha beta is a total derivative of f at x0, y0. So previously we have talked about partial derivatives, and now this is a total derivative. Now before we have while talking about partial derivatives, we had seen that we do not really need x0, y0 to be an interior point, because all we wanted for the partial derivative with respect to x to exist is that a small horizontal line segment passing through x0, y0 should be contained in our region D, and for the purpose of the partial derivative with respect to y to exist, all we wanted was that a small vertical line segment passing through x0, y0 should belong to our region D. But here can we avoid the notion of interior point? Well, perhaps not. Here when we are considering this limit, then hk could be arbitrary. So it could be a point like here, here. So all we need is a small open set containing the point x0, y0, so that we can actually consider this limit. So here it is kind of needed that this point is an interior point, and also we cannot do away with a point which does not really lie on the domain, because we are using the value f of x0, y0. So if it is a limit point which lies outside our domain, we cannot really say that f is defined at this point, because this is beyond the domain of the function f. Okay, so we have talked about what is the total derivative of a function in two variables. Now let us look at this expression somewhat closely. So f is said to be differentiable at the point x0, y0 if we can find a pair of real numbers alpha and beta such that this limit is 0. Now the question is, can we determine this alpha and beta? So if f is differentiable, can we determine this alpha and beta? So is it an easy exercise, or a different question? To show that a function is not differentiable, what do we do? Do we check for all possible real numbers alpha and beta, all possible pairs of real numbers alpha and beta, and show that such limit cannot be equal to 0? Well, this would be a very tough exercise if we really had to do this computation for all values of alpha and beta. But luckily, we can determine the alpha and beta, which I will tell you in a moment, and we will say that this function is not differentiable if the value of the alpha and beta that we are going to determine does not give us this limit to be equal to 0. So let us see how do we compute this alpha and beta. So what we do is that first we let hk to go to the point 0 0 along x-axis. So what we do is that we consider this limit, and take the very special path where we approach origin by fixing k to be equal to 0. So this is not a very standard way of writing this, but for the sake of understanding I have written like this. But now here k is equal to 0, so we can simplify this limit. So limit h tending to 0. So this is equivalent to saying that limit h tending to 0 f of x0 plus h comma y0 minus f of x0 y0 minus alpha h divided by, this is modulus of h, because here we are going to always take the positive square root, and this is equal to 0. And this limit is equal to 0 if and only if limit h tending to 0 f of x0 plus h comma y0 minus f of x0 y0 minus alpha h divided by h is equal to 0. And what does this give us? It gives us that alpha is equal to limit h tending to 0 f of x0 plus h y0 minus f of x0 y0 divided by h. And we have seen this limit before. This is nothing but f x, so the partial derivative of f with respect to x at the point x0 y0. A similar calculation will yield that beta is equal to fy at x0 y0. So here what we do is that we approach origin, we let the pair hk approach the origin along the y-axis. So here we have fixed h to be equal to 0, and let's see. So we will skip some steps. So this becomes limit k tending to 0 f of x0 plus x0 comma y0 plus k minus f of x0 y0 minus, and thus h is equal to 0 here, so we will be left with beta k divided by modulus of k to be equal to 0. And we have seen that this is equivalent to saying that this is equal to limit k tending to 0 f of x0 comma y0 plus k minus etc etc, whatever is written, we replace modulus of k by the quantity k, and this will give us in a very analogous manner that beta is equal to fy at the point x0 y0. So thus we have determined that alpha is equal to fx at the point x0 y0, and beta is equal to fy at the point x0 y0. So what we have proved is that differentiability. We have proved that we have not only determined the values of alpha and beta, we have proved that differentiability at x0 y0 guarantees the existence of the partial derivatives, existence of fx x0 y0 and fy x0 y0. And then what is the pair? What is the total derivative of the function if it exists? Then it is nothing but the gradient of f at the point x0, y0. So you remember that alpha beta that we have just determined was called the total derivative of f at the point x0, y0, and as we have computed, this is nothing but fx x0, y0 comma fy x0, y0. And this is what we had called gradient of f at the point x0, y0. So let us go forward and look at an analog of Carathéodory's lemma that we have seen in our one variable calculus. So what was the statement? The statement was, as always, d is a subset of R, f is a real valued function on D, and C is an interior point of D. So then it turned out that f is differentiable at the point C if and only if there exists a function f1 from D to R that is continuous at the point C and satisfies the equality fx minus fc equal to x minus c times f1x for all x in D. And also we had derived that in such a case f prime c is equal to f1 of c. So this also gives a way of computing the derivative of the function that we started with, and also this function f1 that we just talked about was called an increment function. So we want to see whether we can generalize this notion of Carathéodory's lemma to functions of two variables. So the answer is yes, and we are going to omit the proof for the time being, and we are just going to give you the statement. So as always, D is a subset of R2, which is going to be the domain of our function, and x0, y0 is an interior point of D. We have seen that we cannot do away with the assumption that D is an interior point of D. Then f is said to be differentiable at x0, y0 if and only if there exist two functions f1 and f2 from D to R such that f1 and f2 are continuous at the point x0, y0, and for all pairs xy, all points in D, f of xy minus f of x0, y0, we have that this is equal to x minus x0 times f1x and y minus y0 times f2 xy. Okay, so as I said that we omit the proof for the time being, and if possible we will see this we will have a look at this in our assignments. Okay, so if if the function is differentiable, so then we have seen that these two functions which are analogous to the increment functions in the case of one variable calculus exist, and they are continuous, more importantly at the point x0, y0. Such a pair f1 xy, f2 xy is going to be called a pair of increment functions. Now in one variable calculus we had seen that if an increment function exists, then it is unique, at least at that point it is unique. So because at all the points where the function is going to be differentiable, we were going to have that f prime c is equal to f1c. But here there is a surprise that this function is not unique. So in fact you could take any continuous function g from D to R which is continuous at the point x0, y0, and then we consider this pair g1 and g2 which is defined as follows: g1xy is equal to f1xy plus y minus y0 times g of xy, and g2xy is f2xy minus x minus x0 times g of xy. So if you just put in this information in this equality that we have just observed, you will see that this will work out well, and in particular there will be some cancellations of term, but you will see that fxy minus f of x0 y0 will be exactly equal to x minus x0 times g1xy plus y minus y0 times g2xy. So this possibly gives us infinitely many possibilities of pairs of increment functions. So what is the cardinality of the set of pairs of increment functions? This is the same as the number of continuous functions, or this is at least the same as the number of continuous functions at the point x0 y0 and the functions that are defined on the domain D. Now we come to uh, uh, rather familiar consequence that shows that differentiability of a function at a point x0 y0 implies the continuity of the function at the point x0 y0. So I am going to give only a sketch of this proof. So what we do is that we choose. So if the function is differentiable at the point, so if f is differentiable at the point x0 y0, then we choose a pair of increment functions and we write down the equation that we got by the definition of increment functions. So then what we do is that we apply limit as xy tends to x0 y0 on both sides. So here also limit xy tends to x0 y0 on both sides. So you will see that since the function f1 is continuous at the point x0 y0, this goes to f1 of x0 y0. This goes to f2 of x0 y0. Where does this go to? X minus x0, this go to 0. Where does this go to? Y minus y0, this also goes to 0. So in particular, the limit is equal to 0, and that's all our definition of limit is. So we have shown that a differentiable function is continuous. So we will talk more about differentiability, how to check differentiability, sufficient conditions of proving differentiability of a function, and examples in our upcoming videos.